Hi, my name is Ari Berger and I'm the Chief Technology Officer of Hillcrest Energy Technologies. Thanks for coming back. Today we're going to talk about what's called wide bandgap devices, what the challenges that they introduce into the market, how we have a better solution. It's going to be a bit of a technical discussion, so just bear with me. I'll try to simplify. So the first thing I want to talk about how switching losses actually occur in the inverter. Okay, a bit of physics. Let's see. So let's say I want to turn a switch off. There is current going to a motor, for example, and during that I need to turn off a switch. Let's see how that looks like. So the switch was on. When I turn it off, the voltage across the switch looks like this. It takes time for the electronics to actually open the switch, like we mentioned. This time could be as short as 100 nanoseconds. That's really short time, but during this time there's a lot of heat being produced. While this voltage across the switch, which we call VDS, just for completeness, while this is being turned off, let's see what happens to the current that is flowing through the switch. The current was flowing, and at this point we started to open the switch. We want to open the switch. So the current starts to go down, and when the switch is fully open, then the current is zero because, well, the switch is open. During this transition, in this area, we have this triangle. The area in this triangle is the switching losses. Okay? So that's the basics of switching losses, how they occur, when they occur, and what affects them. So how do we get rid of those switching losses? And that's where I want to talk about wide bandgap devices. Silicon carbide mostly is the most common one. There are others, but currently not in our focus. So let's talk about silicon carbide. Silicon carbide, what happened is that they were able to come up with a material that could switch very fast. So faster than this. And let's see what happens. So let's say that we are able to switch not at 100 nanoseconds, but at 50. The switching will be much more with a much higher gradient. This is something that we call dV over dt. You might hear me say that a few times, dV over dt. That's how fast the voltage is jumping. The current is reacting to that. So the idea is the same, but look what happened now. Because I'm switching faster, the area here is much smaller. Great, you say, right? Let's do that. Well, as it turns out, there are some bad consequences of trying to switch very fast. Basically, nature doesn't like fast transitions. These are really fast transitions. There are phenomena that happens outside of the inverter that are reacting in a very bad way to these fast transitions. For example, the insulation on motor windings. Some of them cannot withstand that high dV over dt. There is something that is called stray capacitance or parasitic capacitance because of the lines and just the layout of the whole system. That parasitic capacitance will react with parasitic current in the system due to this high transition. So we all know that, but what's next? That's how we came up with our solution at Hillcrest. We developed a proprietary technology that is able to maintain a sort of relaxed gradient that the system doesn't negatively react to. So maintain this one, but eliminate the losses here. That's what we do.